I am Shaurya Mahajan, the team captain, and I manage the programming for all three microcontrollers. I've also handled the data collection for our OpenMV camera.
I am Ayan Suri and I manage the robot's hardware and electronics. I have also worked on the 3D design and modeling of our custom 3D printed parts and done the team's documentation. Summary of the challenge. The RoboCup Rescue Line Challenge is designed to simulate a real-life rescue mission. In this challenge, our robot must autonomously navigate through a disaster-like area. Along the way, it will navigate through intersections, seesaws, ramps, speed bumps, and obstacles, earning points for each task completed. It has to rescue victims by placing living victims in the green evacuation zone and dead victims in the red zone. Finally, the robot must stop at the goal tile, completing the entire challenge within 8 minutes. Robot Overview. A robot is designed for reliability, precision, and adaptability. It navigates complex areas with intersection, ramps, and rough terrains while detecting and rescuing victims. It is built with LEGO EV3 and 3D printed parts. It uses 3 microcontrollers, the EV3 as the main brain, Arduino for external sensors, and OpenMV for evacuation zone. To reduce size and weight, we removed the EV3's plastic casing and added external buttons soldered to its PCB and mounted on the handle for easier access. A well-engineered hardware setup simplifies our programming and ensures smooth system communication. The robot uses 2 large motors of 160 RPM to drive the tracks for high traction movement over ramps and speed bumps, and 2 medium motors of 250 RPM to operate the arm for victim pickup and placement. A servo-driven rescue plate enables victim drop-off in the evacuation zone. We use a rechargeable EV3 lithium-ion battery for the EV3 brick. To reduce weight, we remove the casing and excess plastic from the standard EV3 battery. The battery has a capacity of around 2000 mAh, providing power to the EV3. Additionally, we use 2 1500 mAh LiPo batteries to power the 2 Arduino Nanos independently. The arm and claw assembly is a removable module for easy maintenance and upgrades. The arm uses 4 knob gears to operate the claw, with bevel and spare gears transmitting motion to lift and rotate the arm. Robot uses electronics used. We use 3 EV3 sensors, 2 color sensors for line following and detecting intersections, and 1 gyro sensor to handle ramps. On the Arduino, we have used several sensors, a ultrasonic sensor pointing downwards to detect the end of ramps, a modified analog IR sensor to detect the silver line for entering the evacuation zone, a laser time of flight sensor to detect obstacles and victims, a IR/TF sensor on the side of the robot for exit detection, a digital IR sensor to verify a live victim on the rescue plate, a light-dependent resistor with an LED to check for dead victims by detecting reflected light. Communication. The EV3, which functions as the master controller, communicates with the first Arduino Nano over I2C. The first Nano exchanges data with the second Nano via SPI, while the second Nano manages all I2C sensors through an I2C multiplexer. Communication between the second Nano and the multiplexer also uses I2C. The first Nano connects to the OpenMV camera using UART.
For software design, the program has 2 loops. The first measures the gyro tilt in the line following algorithm that checks whether the gyro value is within the range or at an intersection. Otherwise, it runs a proportional line follower. When color sensors detect a value above a certain threshold or the relay is triggered for TOF or OpenMV, the inner loop exits. The board then checks for obstacles, silver tape, or the gold tile. Arduino EV3 communication uses the I2C block on the EV3 to send specific bytes for different cases. If no ramps are detected, the robot checks for intersections. Green squares are detected using the color sensor's advanced RGB mode for accurate reading. Both sensors detecting green indicate a U-turn. Otherwise, the program uses the error value to correct alignment and compares reading to identify single greens. The gyro is also checked to detect greens on ramps. If no double green or single green is found, the robot triggers the pathfinding logic. When no intersection is detected, the robot performs a proportional line follower using two color sensors. It measures each RLI value, calculates the difference, multiplies it by a constant value, and stores the result as an error for course correction. Unregulated motor blocks are used for consistent performance, unlike regulated motors that vary with load or battery. Evacuation zone. When the robot detects the silver tape, it moves forward and spins until the OpenMV camera finds the live victim. If not detected within a time limit, it reverses in the opposite direction for a better view. If the TF sensor detects an object while spinning, the robot backs up to avoid collision. Once found, the robot centers itself to the victim and moves forward until the TF sensor triggers, picks up the ball, and uses a digital eye to confirm its presence. If no ball is detected, this process is repeated, and if detected, the ball is placed successfully on the rescue plate. The robot repeats this for the second alive victim. After both have been placed, it searches for the dead victim, picks it up, and uses an LDR to confirm its presence. After holding the dead victim, it moves to the evacuation points for alive victims, releases them using a servo, and then drops the dead victim at its evacuation point with another servo. Exit. After dropping all the victims at their designated evacuation points, the robot starts its exit detection program. It first moves towards any side of the wall and continues moving until one of the two IR TOF sensor detects an opening or the front TOF sensor detects a wall. If the front TF sensor detects a wall, the robot turns and repeats the process. However, if any other IR TOFs detect an opening, the robot checks whether it is the entry or the exit. If it is the exit, the robot exits the evacuation zone. If it is the entry, the robot repeats the program. Strategies and innovation. We developed a pathfinding algorithm to improve the robot's navigation. It allows the robot to autonomously correct its course during sharp turns, or if it deviates from the line, enhancing overall performance. If the robot loses the line while turning, it reverses the direction for a set number of rotations. This real-time adjustment helps the robot accurately follow complex paths and navigate the line efficiently. We have modified an analog IR that is designed to be compact. This innovative design allows for unrestricted positioning, enabling the IR to be used in various locations to suit different applications. As a result, this adaptability enhances the precision and performance, making it ideal for a wide range of use cases. AI tools used. We have used AI in various ways for the competition. We utilize Canva AI to create captions and design elements for this video. For visualizing the claw's motion and its structure, we have designed and animated the claws in Fusion 360's AI-assisted modeling tools. Earlier, for detecting the victims through the OpenMV camera, we used a model development tool called Edge Impulse for our previous models. Now we label and extract the raw labeled images from the software and train it manually for creating a more accurate and customized detection model. Knowledge sharing. As part of sharing our knowledge, we guide our junior teams at our school in both hardware and software aspects. We continue to use EV3 color sensors and large motor as they are reliable and provide consistent results.